Our final video in this series on acids and their derivatives, we're going to look at acyl halides, which we have come across in previous videos. So acyl halides, first of all, how do you make them? Well, it's a pretty nasty reaction. You have to take sulphur dioxide chloride, which is SOCl2, and react it with the carboxylic acid, and that will replace the OH group with a Cl atom. And also HCl and sulfur dioxide. So you certainly don't want to be doing this in the lab. You need to do it in a fume cupboard, and that would give us propanol chloride. So how do we name these acyl halides? Well, as we mentioned before, you start with carboxylic acid, and then you change the ending to OYL and end with the halide. So you have ethanoyl chloride, propanoyl chloride, and butanoyl chloride. If you have chains coming off, in the example at the bottom there, we've got a 4-carbon chain, so that is butanyl chloride, and that first carbon is always going to be carbon number 1 with the COCl group, and therefore the methyl group is coming off carbon number 2, so it becomes 2-methyl butanoyl chloride. So acyl chlorides are extremely reactive. That's because my carbon is delta positive, and I have a delta negative oxygen and delta negative chlorine. So you have to be really careful with storage. They react with water, alcohols, amines, and ammonia. We're going to go through each of those reactions. Because those halides are really good leaving groups, Cl is very happy to leave a Cl minus. Nucleophilic addition elimination reactions occur. Okay, so what does that involve? Well, here we go. First of all, we've got the nucleophile with an hydrogen attached. So this is just a general nucleophile with a hydrogen, because we're going to need that hydrogen. The lone pair is going to attack the delta positive carbon, and at the same time the carbon-oxygen double bond breaks. Then the nucleophile, that central atom on the nucleophile which has bonded with carbon, will now have a positive charge. Then the lone pair on the oxygen will reform the double bond, and at that same time the carbon-chlorine bond will break to give me the chloride ion. And then finally I need to remove that positive charge on my nucleophile. So the chloride comes along, picks up the H, and the electrons from the nucleophile hydrogen bond go back to the nucleophile, and I form my new acid derivative, and along with HCl. So we'll go through some examples. That's a general mechanism, and we'll see how we can use that in different cases. So this would be the mechanism with H2O, for example. So I've got the nucleophile attacking. I then have, in the second step, the oxygen now has a positive charge. And so when the chlorine comes along, picks up that additional oxygen from the, picks up the additional hydrogen from the oxygen atom. So those electrons can go back to the oxygen. So I form the carboxylic acid, and I form HCl. Alcohol is exactly the same, apart from rather than ending up with an alcohol, I end up with an ester. With NH3, very similar again. All I'm doing is you have the nucleophile, NH3 there, and you end up with the nucleophile attached to the C double bond O, but minus a hydrogen. So exactly the same. The only difference is that because you form HCl, HCl will react with ammonia, because ammonia is a base, and so forms ammonium chloride. So whenever you do that reaction, you would need to double up your quantities of ammonia, because one ammonia will be needed to react with the HCl that's been produced. And then finally, with an amine, again exactly the same. You just produce a amide in this case. In a similar way to ammonia, Amines are also bases, so they will react with HCl to produce a salt.